What's up, mathematicians? In this video, I'd like to take you through some proofs. So, I've got a list of proofs right here. Let's look at the first one first. It says, prove that the sum of two odd numbers must be even. So, I'll take you through two different approaches for this proof. And first approach is algebraic. So, approach number one. Okay, so two odd numbers. So we'll say let x and y be odd numbers. And this is our given. Probably should have. Let me give myself can't even talk. Give myself a little space there. Okay, so this is our given, and our goal is to show that x plus y is even. Okay, so let's start by just thinking about what it means for a number to be odd. And so first we can say, so we can write x as 2n plus 1, and write it down here. Oops. And you can write y as 2m plus 1, where n and m are, well, I'm just going to say natural numbers, but keep in mind that this would work for integers, but I'm going to go ahead and just say, for the purposes of this proof, we'll just be talking about natural odd numbers. So n and m are natural numbers. And why can I say this? So this will be, step one. So why can I say this? It really comes down to the definition of odd number. So I'm just going to say the definition of odd. The reason is that an odd number is always one more than an even number. An even number is a multiple of 2, and so if you take any odd number, it's going to be one more than a multiple of 2. So a number like 17, for example, 17 is equal to, I'll write it this way, it's 2 times 8 plus 1. And so if a skeptic is a little bit unsure about this step, it might take just a little bit of explaining how any odd number that you come up with can be written as 2 times a natural number plus 1. So once we have that, we can do a little bit of algebra. Okay, so that's step one, is we come up with these ways of expressing x and y. And then step two, we'll say note that x plus y is equal to 2n plus 1 plus, so this will be x, plus 2m plus 1. Well, that, of course, is going to equal 2n plus 2m plus 2. Okay. And now we can factor a 2 out of all those things. So I'll go on the next line. So this equals 2 times n plus m plus 1. Well, so I guess I'll say step 3 here. Give myself a little more space. So step 3 is just to note that this is an even number because it is a multiple of 2. So it's 2 times some natural number. N plus m plus 1 is a natural number, because when you add natural numbers, you get other natural numbers. So again, a skeptic might want to question that a little bit, and you could, dig into that. But, most likely, most skeptics would understand that, yeah, if I add 2 natural numbers, I get another natural number. This is known as closure. If you want to get into the sort of algebraic theory behind it, you can look into that. But yeah, basically, natural numbers are closed under addition, which means anytime you add 2 natural numbers, you get a natural number. So this number right here, 2 times n plus m plus 1, must be even because it is a multiple of 2, because it's 2 times a natural number. Okay, so this is the definition of even. Okay, and that's really it, because we've shown that x plus y is even. So therefore, x plus y is even. Okay, and our proof is complete. We'll put an exclamation mark on there. So that's approach number 1. I said that I would show you 2 different approaches. So that's approach number 1. Let's look at a second approach. Give myself a little more space here. So approach number 2. Maybe I'll change colors to make it stand out a bit more. Okay. Approach number 2. So in this case, our given and our goal are the same. So I'm not going to rewrite those things. So given that x and y are odd numbers, show x plus y is even. But I'm going to take a different step 1. So step 1, x, I'll say x and y rather, can be as, and I'm going to sort of use dots here, can be represented as, let me see, I'll do it over here. Let me see, I'll actually do it like this. Represented like this. Okay, so imagine that you have x, okay, and x is the quantity of dots that I have here. And there might be a whole bunch more dots, but in the end, there's going to be a last pair of dots, and then there's going to be a single dot down there. And y can also be represented in a similar way. So pairs of dots, and there might be who knows how many pairs, doesn't really matter, but there will be a last pair. And if it's the number 1, there wouldn't be any pairs at all, right? It would just be that single dot. Either way, there's going to be a number of pairs. It might be 0, it might be 1,000, who knows, and then a single 1 dot left over, and there's going to be a bunch of pairs of dots, and there's going to be a single 1 dot left over. Now understand that this is actually the same thing as saying, as I did in the last proof, 2n plus 1, because this distance right here, this is n rows, basically. And this here is 2m plus 1. But I've seen students come up with this argument with dots because, I don't know, there's something geometric and intuitive about it, right? Okay, so then step 2, oops, let's go back to my green here. So step 2, note that when I add the x and y together, when I add x plus y, I get rows of 2, right? Because I have this many rows, and then over here, you know, oops, that is going to be m rows, right? So I have my n rows plus my m rows. So I get rows of 2 plus 2 more left over. Which make another row of 2. So because I have those 2 left over, and of course we're talking about this one here and this one here, those 2 combine to have some final row of 2. Okay, well, yeah, I'll just keep it there. And so what I'm saying is, you know, x plus y, I'm running out of space. I'll do it horizontally. I can take x plus y, and that can be represented as a bunch of rows of 2, who knows how many, and then at the end, these 2 show up at the end and make yet another row of 2, meaning that it's an even number. Okay, so it's really the same argument, but in the approach number 1, I took a more algebraic, I showed it algebraically, and here I'm just making a little bit more of a visual or geometric, taking a visual or geometric approach to the same argument. But essentially it is the same argument. So yeah, so therefore, oops, I don't have to write therefore. The symbol, the 3 dots mean therefore. So x plus y is even, okay? Yeah, and so, if you have a really particularly harsh or pedantic skeptic, you might have to try to fill in a few more details here and there, but the strategy here is a good one, it's a correct one, and we've seen 2 different approaches to it. Okay, so that's the first of the proofs. Let's go on to the next one. Prove that if n squared is odd, n must also be odd. Okay, so as with most any proof, there are a variety of ways to do this. I want to show you one that I think is kind of interesting because it uses the contrapositive and uses the fact that the contrapositive is equivalent to the original conditional statement. Okay, so I'm going to start by saying, note that n squared is odd implies n is odd is equivalent to the following statement. N is not odd implies n squared is not odd. And this is the contrapositive. Okay, so this is a proof using the contrapositive. And so instead of writing it as you see here, this is how I'm going to write it. So given and by the way, because there are only 2 options here, and I know I'm sneaking in a disjunctive syllogism here, but it's a valid way to reason. Since there are only 2 options for a natural number, it's either odd or it's even. So if it's not odd, it must be even. So I'm actually going to say my given is that n is even, because that's actually saying exactly the same thing as saying n is not odd. And my goal is show that n squared is even. Okay, so I'm just going to show you one approach here. It'll be a pretty straightforward algebraic approach. And so step one, note that n can be written as 2 times a for some natural number a. And this is the definition of even, right? Because an even number can be written as 2 times another natural number. An even number has 2 as a factor, and that's the definition of even. Okay, so we know that we can write n as 2a. Okay, so now let's do a little algebra. Then n squared equals 2a squared, which equals 2a in parentheses squared, which equals 4a squared, which equals 2 times 2a squared. And this is an even number, right? Because it's 2 times some natural number. So because of that, we can conclude that we have an even number. Therefore, n squared is even. And even though it seems like, oh, we didn't actually prove the original thing right here, since we proved the contrapositive, and the contrapositive is equivalent to that statement, we can conclude if n squared is odd, n must also be odd. Kind of cool, huh? All right, so that is part B. Let's go on to the next proof. This is a fun one. I like this one. So this one actually has a little story behind it. But why not? I'll share with you. I was driving with a friend. We were out in was it the Sequoia National Forest, I believe, on a rock climbing trip, and we were out on some dirt roads. And yeah, we had to go ahead and drive down. Yeah, for I forget how far, but maybe 6 miles down some dirt roads. And what happened was, when I looked at the clock, it said it was 3:14 p.m. So I'm thinking, pi o'clock, cool. I wonder how long it's going to take us to drive this dirt road section. We had to drive out and get some water and food because we were going to be back there for about a week or so. And we were running low on supplies. So when we started driving on the dirt road, it was 3:14. And when we got to the paved road, it was 3:41. And I thought, oh, interesting. 14, 41, those digits are switched. And the difference between them is 27, which is a multiple of 9. And then I just started playing around in my head thinking of like, okay, if I take any number, 2-digit number, and I flip the digits, it always seems to give me a multiple of 9. Well, I wonder if I could prove that. Shouldn't be too hard, right? And so this is the argument that I came up with. And actually, before I share that argument, let me also mention that this is a problem where one could use a proof by exhaustion, which is basically just to go through all the possible cases, right? I mean, there are a finite number of 2-digit numbers, so you could write them all out and take the, reverse the digits of each one and take the difference of each one and check them all. And you would have what, 90 different cases to check. So not, wouldn't take you you could do it within it'd take you more than like 5 minutes probably, but it wouldn't take you a crazy amount of time. So you could just do a proof by exhaustion, literally check every single case and verify it that way. But I think that this is a much more elegant way. So this is the approach I took. So basically we'll say given x is a 2-digit number, and maybe I should mention that we're working in base 10 here, but that is so much the standard that probably doesn't even need to be mentioned. Okay, so x is a 2-digit number. Oh, hang on. Our goal here, is to show if y is the number got by reversing the digits of x, then x minus y, I'll say absolute value of x minus y, is a multiple of 9. Okay, so step 1, I'm going to write x as 10a plus b and y as 10b plus a. Now, it might take you just a little bit of thinking to understand why I can do this, but consider that, in the case of x equals, what did I say here, 93? That would be 90 plus 3. And so that would be like saying, okay, 9 would be my a value, so 10 times 9 plus just 3. And for the y value, it would be 3 times the 10 and then the 9 at the end. So 10a plus b is another way of writing a 2-digit number where a is in the tens place and b is in the ones place. And well, then we take the number in the ones place b, we put it in the tens place, we take the number in the tens place a, and we put it in the ones place. So that's what we've done there. So then I can say, okay, the absolute value of x minus y is equal to absolute value of 10a plus b minus 10b plus a. Okay, and this is going to equal, well, let's see. I have 10a minus a, combining like terms. So this equals the absolute value of 9a. And then we have b minus 10b. So this is minus 9b. Okay, so the absolute value of 9a minus 9b. Okay, so this equals the absolute value of 9 times a minus b. And in this case, I could even just write the 9 outside the absolute value sign. It doesn't change anything. So I take the 9 times the absolute value of a minus b. So there we go. Let me make this look a little more like a 9. Okay, so that's it. That's the proof. Therefore, x minus y, absolute value, is a multiple of 9. And if you're not convinced, spend a little more time thinking about it. But basically, you can see how we started with x minus y, and we ended with 9 times a minus b, where a and b are going to be whole numbers, natural numbers in this case. And so we see that we have 9 times a number, a whole number, which means that it's going to be the resulting sum will be, or the resulting number will be a multiple of 9, which is exactly the thing we're trying to prove. So I think that's a nice, elegant little proof, quicker than the proof by exhaustion. And yeah, it's a nice little proof to go through as well. All right, so I think that I want to pause it here and make a second video. See, these next few proofs have a different sort of strategy or idea behind them. So I'm going to pause it here and make a separate video with the next 3 proofs. So I hope this was interesting and helpful, and hope to see you in a future video. Bye-bye.